The next topic that we will be looking at is combustion reaction. Now we have actually solved a few examples about combustion before this, but in this topic, in this section, we'll be looking at few important terminologies about combustion. The first thing is that combustion can be defined as the rapid reaction of a fuel with oxygen to produce energy and other gaseous products. Now some of the examples of fuel used in power plants are coal, fuel oil, gaseous fuel such as natural gas, which is primarily methane, and also liquefied natural gas, LPG, which usually contains propane or butane. So some of the examples of combustion reaction is the natural gas used to generate electricity, engine used to combustion of petrol and diesel. Based on the definition of combustion, our fuel will react with oxygen. Now, we would like to find the cheapest and most common source of oxygen, and air is the most common and cheapest source of oxygen. And if you look at the composition of air contains nitrogen gas, oxygen gas, carbon dioxide, carbon monoxide, and other gases. But in our case here, to make our calculation easier, we can assume that air only have 79% nitrogen and 21% oxygen. And we can say that the average molecular weight of air is 29 gram per mole. Now, we also make another assumption that nitrogen that we have in our air is treated as a non-reacting component, which means that it is considered as inert by neglecting the oxidation of N2 to NOx. So this one actually, if you are reacting at a very high temperature, there is a possibility that nitrogen can react with oxygen to produce nitrogen NO2, NO, and other forms of NOx. So in our case, we just say that nitrogen is an inert and will not take part in our combustion reaction. Now, here we have a very important terminology. The first one is that complete combustion. Now, complete combustion is defined as the complete reaction of fuel to form CO2, H2O, water vapor, and other gases. Now, these other gases usually will be depending on our type of fuel. As we looked at before this, our fuel can be coal, LPG gas, natural gas, and so on and so forth. So sometimes those fuel will have some impurities which will create this gas. Okay, and then the second one is partial combustion. Now, partial combustion is defined as combustion of fuel that produces at least some amount of CO. Meaning that if you have a partial combustion, CO will produce together with CO2. So in that case, we'll have two reactions. One reaction for complete combustion and another reaction for partial combustion. As we mentioned earlier, when we have our combustion reaction, we produce some gaseous product. Now this gaseous product is usually known as stack gas. Now this stack gas can be defined on a wet basis or on a dry basis. So if you remember, our product for a complete reaction will be CO2, for partial reaction will be CO, and will definitely have water. So the term composition of weight basis is commonly used to denote the component or mole fraction of a gas. So this gas, stack gas, that contains water. So if we include all the product in our stack gas and we include water together, so we'll have the composition in a wet basis. But if we remove the water, then we'll have a dry basis. So the term composition on a dry basis signifies the component mole fraction of the same gas without any water in it. So for example, let us look at a gas that contains 33.3 mole percent of CO2, 33.3% of nitrogen, and 33.3% of water vapor is considered on a wet basis. So having this, so if I were to just write here, if I have my stack gas here contains CO2, N2, which is inert, and also H2O. So this is actually a complete combustion reaction. Now this gas known as stack gas, right? And the composition here, since we are including water, so this is our wet basis. Okay, but the same composition, if I were to remove water here, so if I remove water, I'll be only left with carbon dioxide and nitrogen. This is still your stack gas, but this is on a dry basis because we don't have any water component inside here. Okay, so if you were to look at this, the composition that we have here, so on a wet basis, let's say our product is 100 mole, okay, 100 mole of stack gas. So in that 100 mole, we know that based on this composition of weight basis, we have 33.3 mole of CO2, 33.3 mole of N2, and 33.3 mole of H2O vapor. So if you add up this one, you should be getting 99.9, which is almost 100. Okay, so this is our 100 mole. Now, if let's say I remove my water here, remove my water because I want to get a dry basis composition. So for dry basis, we say that we only have CO2 and nitrogen. So my total mole will become 66.6 mole. Right? So I will get 66.6 mole. Now if I want to get the composition of CO2, I will have 33.3 divided with my total mole is on the dry basis, excluding water, is 66.6 times 100. So I will get 50%. So this is the meaning of when you have a gas with 33.33 mole of CO2, 33.3 mole of nitrogen, and 33.3 mole of oxygen on a wet basis, it will have 50% of CO2 and 50% of nitrogen on a dry basis. The next thing we'll be looking at is our theoretical air and theoretical oxygen. Now, if you remember, when we have a feed, so let's say this is our reactor, a combustion reactor, we'll have a fuel coming in. So let's say this is your fuel, and we will also have air coming in here, right? And in our air, we'll have 0.21 oxygen and 0.79 nitrogen. Okay, this is the mole fraction of oxygen and nitrogen in air. So in order for us, let's say we just say that methane, CH4 plus oxygen, we produce a complete combustion reaction is CO2 plus H2O, right? So to balance our equation, I need to put 2 here, and then I can just put 2 here. Okay, so theoretical air or theoretical oxygen is defined as the minimum amount of air or oxygen required to complete the combustion reaction. So meaning that if I have 1 mole of methane, I will need 2 mole of oxygen in order for me to finish up all my methane. So this is the meaning. I need a minimum requirement of air or oxygen for a complete combustion reaction. So the theoretical oxygen I need here is 2 mole of oxygen. And then, because we know that oxygen is only 0.21% of air, and when we are doing combustion, we are putting in fuel with air because air is a cheap source of oxygen. So in order for us to know how much oxygen is needed, we need to know how much air is needed. And most of the time, because this is our valuable fuel. This is a cheap reactant. So we will always put more air than needed. If I have more air than I need, I will have more oxygen than I need. Then I will make sure that this is my limiting reactant, and this will always be my excess reactant. But in this case, we will only look at excess air. Okay, so excess air is defined as air provided in excess of that required for a complete combustion. So again, if I have excess air, I will have excess oxygen. If I have excess oxygen, I can make sure that all of my fuel will be reacted, will be combusted. Now, a few important things that you need to take into account when dealing with excess air is that excess air is calculated based on how much fuel can be burned, meaning that maximum amount of fuel that can be burned, not how much fuel is actually burned. Okay, so what does this mean? So for example, we look at our equation here. Methane plus 2 oxygen will get you CO2 and H2O. So for example, we know that, let's say in our feed here we have 10 mole of methane. 10 mole of methane. Okay, so in order for me to react completely 10 mole of methane, I will need 20 mole of oxygen, right? But for me, since I know oxygen is available in air, so I will want to put more oxygen in it. So I can put maybe 30 or 40, right? So maybe I put here 40 more. So now I know that my oxygen is in excess, which means that my air is in excess. But how much excess air you want to calculate is based on how much fuel can be burned. Meaning that even if I say that the conversion of my methane here is only 50%, right? 50% conversion, meaning that only 50% of methane will be reacted. Even if this is 50%, then if let's say if I am reacting 5 mole of methane, based on this, only 5 mole of methane will be reacted. So I will only need 10 mole of oxygen, right? 10 mole of oxygen. So even though this is the amount I need, but I will always calculate my excess air based on what is the maximum amount of fuel that I can burn. So we won't consider our conversion here. We'll be only looking at what is the feed of methane that we have. And based on that, we'll calculate our excess air. Excess air meaning here, if you want to have 20%, 30%, 40%. So based on that, you will have to understand that this is what we will be referring to when we are calculating excess air. And the second thing is that if you have both CO and CO2 form in the reaction, meaning that we have a partial combustion reaction. So this is from partial, this is from complete combustion reaction. Theoretical air and excess air are calculated assuming all fuel is burned to form CO2. Meaning that, so let's say I have two equations here. My first equation is methane plus oxygen will produce CO plus H2O. And then my second equation is that CH4 plus O2 will produce CO2 plus H2O. So I can put here 2, and then this one will be 1.3 over 2, and then 2. So even if we have partial combustion, so in order for us to calculate our excess air, we will only consider this reaction. We will not consider this reaction. So this is the meaning of this statement. So the excess air and theoretical air are calculated assuming all fuel is burned. So it doesn't matter if you have a partial or complete combustion. When you are calculating excess air and theoretical air, you just focus on this complete combustion, and you focus on that saying that all fuel is burned. So you want to have the maximum amount of oxygen possible. So if we have a maximum amount of oxygen, then we also have the maximum amount of air possible. And the equation to calculate percent of excess air is mole of air that is actually fat. So this is the thing that we want to find. Okay, how much mole of air is fat? Because if you find how much mole of air is fat, then we can find how much oxygen is fat. Minus mole of air theoretical. So this can be calculated based on our stoichiometry, divided with our mole of theoretical times 100. So this is the formula to calculate percent of excess air.